A newly welded Liberty ship slid down the Burrard dry dockways after only 10 days of construction. Steam rose from fresh welds still cooling in the December air. 3 days later, a sister ship launched across the harbor at North Van Ship repairs. Within a week, both joined an Atlantic convoy carrying munitions and aircraft engines destined for Britain. In Berlin, German naval intelligence noted impossible numbers. Allied yards were producing more cargo tonnage per week than U-boats could sink per month. Grand Admiral Karl Donitz's command had calculated replacement rates at 1 ship for every 4 lost. But Canada and the United States had reversed that ratio entirely. The Kriegsmarine's logistics war, once its strongest weapon, was collapsing under the weight of an unexpected industrial rival from the Pacific coast. This is how Vancouver's modular shipyards transformed steel, welding, and urgency into the fastest maritime production system in the world. On the desk of Minister of Munitions and Supply Clarence Decatur Howe lay a memorandum titled Park Ship Program, Emergency Wartime Construction. The document bore routing stamps from Treasury Board, Wartime Shipping Limited, and Canadian National Railways. Each stamp represented another layer of bureaucratic approval, compressed into weeks rather than the usual months or years. The plan was ambitious beyond anything Canada had attempted. 117 standardized cargo ships, each approximately 10,000 tons displacement, all welded to United States Liberty-class specifications using standardized blueprints, interchangeable components, and centralized procurement systems. The budget line read 140 million Canadian dollars. In 1941, this represented an enormous commitment for a nation of 11 million people. A staffing note estimated 18,000 workers required on the Pacific coast alone. This was more workers than had ever been employed in British Columbia's entire shipbuilding industry throughout its history. Burrard Dry Dock of North Vancouver was selected as the primary flagship yard. The choice was logical but daunting. Burrard had experience with ship repair and small vessel construction. But ocean-going cargo ships on this scale? That was unprecedented. At that moment, Canada possessed only 3 operational slipways capable of handling ocean-going tonnage. British Columbia's industrial base was built for lumber, fishing boats, and coastal trade, not steel fabrication at industrial scale. The province's economy centered on forestry, mining, and agriculture. Heavy manufacturing was minimal. Skilled shipbuilders were almost non-existent. German intelligence analysts reviewing the announcement estimated it would take Canada at least 24 months to produce 1 ocean-going hull from a standing start. Their assessment wasn't unreasonable. Building an industrial base from scratch typically required years. Training workers took time. Establishing supply chains demanded infrastructure that didn't exist. But C.D. Howe had different ideas. His ministry coordinated with Wartime Shipping Limited to streamline every aspect of procurement. Steel plate would come from Algoma Steel in Ontario. Boilers and turbines from Montreal and Sorel in Quebec. Hamilton foundries would supply deck fittings, windlasses, and anchors. The Canadian National Railway received priority routing codes for westbound shipments carrying ship materials. Every potential bottleneck was identified and addressed with central planning authority that only wartime emergencies could justify. The target seemed impossible to industry veterans. But Ottawa scheduled production against Liberty-class specifications with a standardized bill of materials. Centralized procurement eliminated redundant bidding processes that normally consumed months. Rail priority codes ensured steel moved west without delay waiting for commercial traffic. The plan wasn't just ambitious. It was mathematically precise. Every ton of steel was accounted for. Every component was scheduled. Every worker position was planned. The organizational chart resembled a military operation more than traditional commercial shipbuilding. And that was deliberate. C.D. Howe understood that wartime construction required military discipline applied to industrial production. Peacetime methods wouldn't suffice. By September 1942, reality began to overtake skepticism. The first Vancouver keel was completed in 41 days from laying to launch. The ship was real. The hull was sound. Classification surveyors certified it fit for Atlantic crossing. That same month, the Bremen shipyards, Germany's primary U-boat construction facility, launched only 5 new U-boats. The tonnage war had begun. But Germany didn't yet realize the scale of what was assembling on Canada's Pacific shore. They saw the announcement of Canadian shipbuilding plans as propaganda, the kind of optimistic projections that democratic governments issued to maintain morale but rarely delivered. They would learn otherwise. Surveyors chalked new slipway centerlines over timber wharves where fishing boats had once tied up. Piling crews drove foundations where log booms had floated just months earlier. The transformation was total and relentless. Lumber docks became steel fabrication halls. Fish processing areas became welding shops. Warehouse space converted to pipe fitting and electrical assembly stations. Burrard Dry Dock expanded from 22 acres to 60 acres of intensive industrial development. 11 slipways were constructed, each capable of handling 10,000-ton hulls. 250-ton traveling cranes were installed on rails, allowing them to serve multiple workstations. Traversers, massive railway-mounted platforms capable of moving hull blocks weighing hundreds of tons, were positioned along railway sidings that connected directly to Canadian National Railway main lines. The scale of construction rivaled the shipbuilding itself. Thousands of pilings were driven into the harbor bottom. Hundreds of tons of structural steel formed crane gantries. Miles of electrical cable powered welding stations, lights, and crane motors. Compressed air lines, oxygen lines, and acetylene distribution systems created an industrial infrastructure from nothing. Yard Superintendent A.F. Heath oversaw the conversion with engineering precision. His background combined marine architecture with industrial management, exactly the hybrid expertise needed. His approach differed fundamentally from British methods that had evolved over centuries. Traditional yards in Britain used open-air assembly with rivet-centric construction. Ships were built linearly on slipways exposed to weather. Winter rain meant delays. Summer heat meant expanded metal and dimensional challenges. Workers competed for space on cramped slips. Skilled riveters commanded premium wages and worked at their own pace. Heath planned enclosed prefabrication sheds that would allow winter-agnostic throughput regardless of weather. The concept borrowed from automobile manufacturing. Henry Ford's assembly line principles applied to ship construction. If cars could be built from subassemblies in controlled environments, why not ships? An internal memo from March 1942 explained the philosophy. Sections are built complete with plumbing and wiring before they ever see the slip. This was revolutionary in maritime construction. In British yards, ships were built linearly from keel up. First, the keel was laid. Then frames were erected sequentially. Then plating was added piece by piece. Then internal structure followed. Finally, outfitting began. Each stage had to wait for the previous stage to complete substantially. Weather delays cascaded through the entire schedule. Skilled trades competed for workspace on cramped slipways. A single bottleneck could idle hundreds of workers. Vancouver's approach parallelized the work. Hull sections could be fabricated in one shed, deck houses in another, engine room assemblies in a third, pipe spools manufactured to standard specifications in a fourth, electrical harnesses assembled on benches in a fifth, all simultaneously, all under the roof, all proceeding on independent schedules that converged only during final assembly. Only the final assembly happened outdoors on the slipways, and even that was accelerated because the pieces arrived nearly complete. Joining prefabricated blocks took days instead of the weeks required for traditional construction. Canadian National Railway block trains began delivering approximately 1,000 railcars per month. The trains arrived on dedicated sidings. Gantry cranes unloaded steel plates directly into fabrication sheds. The material flow was continuous. No warehouse delays. No inventory buildups. Steel moved from railcar to workstation within hours. Dominion Oxygen engineers surveyed the site and immediately recognized the scale of demand. Welding on this scale would require industrial oxygen supplies that didn't yet exist on the West Coast. Existing oxygen plants served smaller industrial customers, metal fabricators, hospitals, chemical plants. But ship construction at Vancouver's planned scale would exceed their combined capacity. Dominion Oxygen began planning a dedicated plant at New Westminster specifically to serve the shipyards. This was industrial logistics planning at regional scale, not just building ships, but building the infrastructure to support building ships. The logistics were staggering, but they worked because central planning eliminated market inefficiencies. In peacetime, each decision would require negotiation, contracts, financing, and competitive bidding. In wartime, C.D. Howe's ministry simply directed resources and authorized construction. Moving pipe fitting, electrical work, and outfit tasks under roof before sections reached the slip reduced the critical path time dramatically. Every day saved on the slipway meant another ship could begin construction sooner. The mathematics compounded. 5% faster construction didn't mean 5% more ships. It meant continuous production with no idle time between launches. By April 1942, cost sheets showed approximately 30% lower assembly cost per ton than British comparators. This was just 6 months after groundbreaking. 6 months after most of the workforce had been hired. 6 months after the first steel arrived. The skeptics had predicted years of learning curves and false starts. Naval architects expected quality problems. Marine engineers anticipated structural failures. Classification societies prepared for intensive remedial inspections. Instead, Vancouver was already outperforming established shipyards with centuries of tradition. The hulls passed inspection. The welds met standards. The ships were sound. And the pace was accelerating. Inside the training hall, arc flash flared across metal coupons. The bright blue-white light illuminated faces protected by welding masks. Instructors marked bead penetration angles on chalkboards, demonstrating proper torch positions and travel speeds. Students, most of whom had never held a welding torch before last month, practiced on scrap steel under close supervision. The workforce statistics were remarkable and unprecedented. 60% of new hires had no shipbuilding background whatsoever. They came from logging camps, farms, retail shops, and offices. They were farmers, clerks, mechanics, and laborers. Some had metalworking experience from unrelated industries. Most did not. Women comprised a rapidly growing share of the workforce, shattering pre-war employment norms. By January 1943, employment rolls would list approximately 1,600 women welders. This represented not just a practical response to male labor shortages, though that was certainly a factor, but a fundamental recognition that industrial-scale production required every available hand regardless of pre-war social conventions. Dominion vocational schools established accelerated training programs specifically designed for shipyard work. The curriculum focused on specific tasks rather than comprehensive shipbuilding knowledge. A welder didn't need to understand naval architecture. They needed to run consistent beads at proper angles with correct penetration. A pipe fitter didn't need to grasp hydrodynamics. They needed to cut, thread, and join pipes to specification. This task-specific training allowed rapid skill development. Traditional apprenticeships required years because apprentices learned the entire trade. Vancouver's training produced specialists in weeks. The specialization was only possible because standardized designs and modular construction broke complex ships into simple, repeatable tasks. Visiting Admiralty inspectors arrived from Britain expecting chaos. British shipbuilding tradition emphasized master craftsmen with decades of experience passing knowledge to apprentices over years. The British system produced superb individual workers with comprehensive understanding of their trades. But it didn't scale quickly. Instead of chaos, the Admiralty inspectors found systematic skill transfer at industrial scale. The process was organized, measured, and continuously improved. Training methods were documented. Successful techniques were standardized. Problems were identified and corrected systematically. The secret wasn't traditional apprenticeship. It was process engineering applied to human skill development. Standard welding procedure specifications eliminated guesswork. Every joint type had a documented procedure. Every material had specified parameters. Welders followed the specifications. Quality control verified results. Deviations were caught immediately and corrected. Jig fixtures held pieces in correct alignment automatically. Workers didn't need years of experience to position components accurately. The jigs did it for them. Positioners allowed welders to work at optimal angles rather than contorting into awkward positions that produced inconsistent results. The fixtures embedded expertise into hardware. Shift rotation kept block assembly lines running continuously. First shift fabricated components. The second shift assembled them into blocks. Third shift finished and inspected. The continuous operation meant learning happened faster because problems and solutions cycled through quickly. A welding technique that worked well in the morning could be taught to the next shift by afternoon. Wartime Commission Report Number 27 documented the results with precision. Productivity rose from 0.9 tons of steel welded per shift to 3.0 tons per shift within just a few months. This wasn't gradual improvement over years. It was transformed through an industrial method compressed into weeks. The improvement curve astonished observers. Initial productivity was low, as expected with inexperienced workers. But instead of the gentle upward curve typical of traditional skill development, Vancouver's productivity rose steeply. The systematic training, standardized processes, and continuous operation created a feedback loop that accelerated learning beyond conventional rates. A British observer noted in his official report, Canadian yards achieved within 6 months what took Britain 2 years of painful experience during the previous war. The explanation was simple but profound. Traditional shipbuilding relied on master craftsmen passing knowledge to apprentices over years of observation and practice. The knowledge resided in people's heads and hands. Scaling required finding and training more masters, which took years or decades. Vancouver substituted repeatable process control for scarce skilled labor. The jigs and fixtures embodied the knowledge. The welding procedure specifications codified the expertise. The training programs transferred essential skills. Workers executed the process. Quality came from the system, not individual virtuosity. This had implications beyond shipbuilding. It demonstrated that industrial methods could penetrate crafts previously thought dependent on traditional skills. If ships could be built this way, what else could be systematized and scaled? By late 1942, this inexperienced labor force was launching ocean-going cargo ships on 5-week cycles. Ships that could cross the Atlantic through winter storms. Ships that could carry tanks, aircraft, ammunition, and food to Britain. Ships certified by classification societies as sound for service. Ships that would determine whether the U-boat campaign succeeded or failed. The workers understood they were contributing to victory. National Film Board cameras documented their work for propaganda purposes, showing women welders and young men operating cranes. But the propaganda was backed by substance. The ships were real. The schedules were met. The quality was certified. They were building the weapons that would win the Battle of the Atlantic. And they were doing it faster than anyone, including themselves, had thought possible just months earlier. The learning curve wasn't slowing. It was still accelerating. A 60-foot mid-body block inched forward on rollers, moving with mechanical precision despite its enormous mass. Overhead, the whir of electric motors filled the cavernous fabrication shed as a traveling crane slewed into position. The crane operator adjusted controls with practiced movements, aligning the hook with lifting points welded to the block's upper corners. The block weighed approximately 200 tons. But weight wasn't its most remarkable characteristic. This block contained completed compartments with installed piping, finished electrical runs properly bundled and secured, and painted bulkheads ready for service. It was a finished section of ship, not a rough assembly requiring extensive further work. It was ready to join the hull and immediately contribute to the vessel's capability. This was the death of linear construction methods that had dominated shipbuilding for centuries. Traditional shipbuilding started with a keel laid on blocks at the center of a slipway. Frames were erected perpendicular to the keel, one by one, creating the skeleton. Plates were added sequentially, starting from the keel and working upward and outward. Trades worked in sequence, structure first, then internal framing, then piping, then electrical, then finishing. Each step waited for the previous step to complete substantially. Pipefitters couldn't work until the structure was in place. Electricians waited for pipes to be installed so they knew where to route cables. Painters waited for everyone else to finish. The critical path was long and vulnerable to disruption. Any delay cascaded through all subsequent operations. Vancouver's hull planning office had divided the Liberty-type design into approximately 250 prefabricated modules. Some weighed as much as 250 tons each. The division wasn't arbitrary. It reflected careful analysis of which sections could be fabricated independently and how they would join during final assembly. Automatic welders adapted from United States Kaiser yard practice joined sections with unprecedented speed and consistency. These machines produced welds of uniform quality, eliminating the variability inherent in manual welding. The operators required less skill than traditional welders. They positioned the equipment and monitored the process rather than controlling every aspect of the weld directly. Dimensional control came from steel templates manufactured to engineering tolerances. Every frame, every plate, every component was checked against templates before welding. This prevented the accumulation of small errors that plagued traditional construction where each piece was fit to the previous piece. Dimensional accuracy was maintained throughout construction rather than requiring extensive fitting and adjustment during final assembly. Every block was shot blasted and primed before leaving the fabrication shed. Surface rust was removed mechanically. Protective primer was applied in controlled conditions. This was impossible in traditional construction where most of the hull wasn't accessible for proper surface preparation until launch. Vancouver's blocks arrived at the final assembly already protected against corrosion. Quality problems were caught and fixed under the roof, not on the slipway. A welding defect found in the fabrication shed could be repaired immediately without disrupting other operations. The same defect discovered during final assembly would require working around other trades, potentially delaying multiple operations simultaneously. The cycle time ledger told the story with stark clarity. In 1942, average construction time was 180 days from keel to launch. By early 1943, that figure had collapsed to 36 days. This wasn't incremental improvement, it was a factor of 5 reduction in construction time. The implications were strategic and immediate. Multiple critical paths now ran concurrently under the roof. 5 or 6 ships could be under construction simultaneously in different stages. 1 ship on the slipway for final assembly. 2 or 3 ships in block fabrication. Another having sections painted and prepared. Another having engine room blocks completed. Production became continuous rather than sequential. Weather risk was removed entirely from most construction phases. Rain didn't stop work in enclosed fabrication sheds. Wind didn't prevent crane operations under the roof. The cold didn't slow welding in heated facilities. Construction proceeded in January as effectively as in July. This consistency was impossible in traditional open-air shipyards where weather determined productivity. Rework was localized to individual blocks rather than disrupting the entire ship. A dimensional error in one block could be corrected without touching other sections. In traditional construction, an error often required rework that rippled through adjacent structures because everything was interconnected. Cranes and welders never sat idle waiting for previous work to complete. Materials arrived on schedule. Components were staged properly. Workstations were supplied continuously. The efficiency approached automotive assembly line standards, unprecedented in shipbuilding. The German trade press still labeled Vancouver's methods. Experimental articles questioned whether welded hulls could survive Atlantic storms. Engineers debated whether prefabrication compromised structural integrity. Naval architects argued that traditional methods existed for good reasons and that departing from proven practice risked catastrophic failures. They published skeptical analyses questioning whether welded hulls could survive Atlantic storms. Some German engineers predicted wholesale structural failures once winter weather tested the hulls. Others suggested that quality control was impossible at Vancouver's construction pace and that defects would emerge in service. Meanwhile, convoy manifests grew longer every month. Vancouver-built ships crossed the Atlantic successfully. They unloaded in Liverpool and Glasgow. They returned for another voyage. No catastrophic structural failures occurred. No quality crises emerged. Just steady, relentless tonnage delivered on schedule. The experimental yards were outproducing the established maritime powers. And the gap was widening every week as learning curves continued driving improvements even after the dramatic initial gains. In the radiography bay, X-ray film racks were clipped to a longitudinal seam running the length of the ship's hull. Non-destructive testing technicians would expose the film, develop it in the darkroom adjacent to the bay, and examine the images for internal defects invisible to the naked eye. These welds would hold against Atlantic storms, generating forces that would tear apart lesser construction. They would absorb shock from near-miss torpedo detonations. The quality had to be absolute. Every major structural joint received this level of inspection. Magnetic flux testing caught surface defects, cracks, porosity, incomplete fusion. Radiography revealed internal flaws, slag inclusions, void spaces, inadequate penetration. The quality control regime was systematic and uncompromising. Ships didn't leave Vancouver with questionable welds. They were certified fit for service or they didn't sail. All-welded hull construction represented a complete break from maritime tradition stretching back a century. Riveting had dominated shipbuilding since iron replaced wood as the primary structural material. Rivet gangs, consisting of heaters, catchers, drivers, and buckers working in coordinated teams, represented the aristocracy of the shipyard trades. A skilled rivet crew was valuable and expensive. Rivet work was loud, hot, dangerous, and required years to master. Vancouver eliminated approximately 7,000 rivets per hull by switching to all-welded construction. Each rivet that didn't need to be installed saved time and labor, but the benefits extended far beyond simple labor savings. The weight savings approached 200 tons per ship. Rivets added weight both from the rivets themselves and from the overlapping plates required for riveted construction. Welded hulls used but joints that required no overlap. The cumulative weight reduction was substantial. At convoy speeds of approximately 8 to 10 knots, this weight reduction translated to approximately 2% improvement in fuel consumption. The lighter hull displaced less water, generating less resistance. The ship could carry the same cargo using less fuel, or carry more cargo using the same fuel. Over a full Atlantic crossing of 3,000 nautical miles, 2% fuel savings meant thousands of gallons. Multiply by hundreds of ships making multiple crossings and the fuel savings became strategically significant. Fuel saved on one ship could power escorts or merchant vessels that otherwise would have waited in port. But the real advantage was labor and time. Welding was fundamentally faster than riveting. A skilled welder could join plates in minutes that would have required hours for a rivet crew. Training welders took weeks, not the years required for competent riveters. The quality control was actually superior to riveted construction. Radiography could find defects invisible to the eye, internal voids, incomplete fusion, slag inclusions. Magnetic flux testing caught surface cracks before they propagated into structural failures. Visual inspection of rivet heads revealed little about the quality of the connection inside the joint. Welding inspection technology exceeded riveting inspection capability. The United States Maritime Commission issued a bulletin calling Vancouver the cleanest hull line in the Allied fleet. Defect rates ran below 1.2% across all inspected welds. This was better than riveted construction, achieved by workers with minimal experience, in yards built from scratch within a year. The systematic process control produced results that exceeded traditional craftsmanship. A classification surveyor noted in his detailed report, "These hulls are better than traditional construction. The all-welded design eliminates thousands of potential leak points. Water can penetrate around rivets that loosen in service. Welded joints form continuous barriers. The inspection regime catches problems before they reach sea that would have been invisible in riveted hulls until failure occurred." The technical superiority was clear to anyone examining the evidence objectively. But skepticism persisted in some quarters. British Admiralty engineers trained in traditional methods questioned whether welded hulls would hold up over years of service. German naval architects dismissed the entire approach as improvisation born of desperation rather than sound engineering practice. Both sides were proven wrong by operational experience. Vancouver-built hulls served throughout the war and beyond. They survived Atlantic storms that would test any construction. They absorbed damage from near-miss weapons. They aged gracefully in service. The welded construction proved not just adequate but superior for merchant service. The arithmetic was simple but devastating to German calculations of how long the tonnage war would take to win. Every day saved in construction meant 7,000 tons of cargo reaching Britain sooner. A 20-day reduction in build time meant that cargo arrived nearly 3 weeks earlier. Multiply by dozens of ships and the aggregate impact measured in months of supply delivered ahead of German expectations. Every percentage point of fuel savings meant more cargo per ton of oil consumed. When Britain faced fuel shortages, every gallon mattered. Ships that used 2% less fuel could make more voyages with available fuel supplies. The efficiency gains compounded with the speed gains to produce effects far beyond what simple arithmetic suggested. Every improvement in quality meant fewer ships lost to structural failure. Every ship that didn't break apart in storms was a ship that completed its mission. Every avoided structural casualty meant cargo delivered, crews saved, and replacement capacity freed for other needs. The modular welded hull wasn't just an innovation or an interesting technical experiment. It was a strategic weapon that directly attacked German calculations of how long Britain could hold out. And Germany had no counter to it because their own shipbuilding industry remained locked in traditional methods without the capacity or resources to undertake fundamental transformation. Two flags flew on opposite shores of the harbor, visible to each other across the water. Burrard Dry Dock on the south side, North Vancouver Ship Repairs on the north side. Chalkboards at each yard entrance posted the latest launch dates in numbers large enough to read from across the street. The competition was intense, public, and remarkably productive. North Vancouver Ship Repairs delivered SS Fort Rouge in approximately 22 days from keel to launch. The accomplishment was trumpeted in the local newspaper. Workers celebrated. Management issued a press release. The achievement set a new standard that seemed almost unbreakable. Burrard responded within weeks, launching SS Fort St. James in 28 days. While 6 days slower than Fort Rouge, the Fort St. James was actually a more complex variant with modifications for military cargo. The competitive response was noted across the harbor. Stakes were raised again. Local newspapers dubbed the phenomenon the 4-week fleet. The name captured public imagination and stuck. Workers wore it as a badge of pride. Recruitment posters featured the slogan. The terminology entered common usage. Vancouver's ships became known globally as the 4-week fleet, a designation that carried implications of speed, efficiency, and industrial prowess. The competition wasn't just publicity or workplace morale building, though it served both purposes. It drove genuine innovation at operational level. Foremen studied each other's methods. Superintendents analyzed rival yard launch announcements to deduce process improvements. Workers who moved between yards carried techniques with them, cross-pollinating both facilities with best practices. Shift scheduling was optimized to keep multiple blocks moving simultaneously without interference. Morning shift fabricated bottom blocks. The afternoon shift worked on deck sections. Night shift assembled blocks into larger modules. The continuous choreography minimized idle time and bottlenecks. Deckhouses arrived at final assembly pre-outfitted with berths, galley equipment, and ventilation already installed. In traditional construction, these fittings would be installed after the deckhouse was positioned on the hull, a time-consuming process requiring multiple trades working in cramped spaces. Vancouver's deckhouses were complete units requiring only connection to ship services. Standardized pipe spools eliminated field measuring and cutting. Piping layouts were designed once, then manufactured repeatedly to templates. Spools arrived labeled and sequenced. Installation required only positioning and welding end connections. The standardization dramatically reduced skilled labor requirements and accelerated installation. Traveling cranes were choreographed to block readiness so critical paths never stalled waiting for lifts. Crane operators worked from schedules showing when each block would be ready for movement. Multiple cranes could work simultaneously without interference because paths were planned to avoid conflicts. The coordination approached railway dispatch levels of precision. The mid-year production summary for 1943 recorded results that would have seemed impossible 2 years earlier. 15 ships were delivered to service. 17 under construction on slips or in block assembly. Cumulative tonnage approximately 160,000 gross registered tons. Average build time below 5 weeks. Quality defect rates below 2%. On-time delivery exceeded 95%. German propaganda outlets dismissed these figures as statistical deceit. The Reich Propaganda Ministry published analyses claiming the numbers were physically impossible given known shipbuilding productivity standards. They calculated man-hours per ton based on German yard experience. They compared to established German yards like Blohm and Voss. Their mathematics said Vancouver's claims were fabrications designed to mislead German planning and boost Allied morale. Then the next month's convoy lists arrived. British port authorities recorded arrivals with ship names, tonnages, and registry numbers. Lloyd's Register documented new hulls with construction details and builder identification. The convoy manifests listed cargo received. The numbers matched Vancouver's claims line by line, ship by ship,
ton by ton.
Intelligence analysts in Berlin had to revise their estimates. Either their fundamental assumptions about shipbuilding productivity were wrong, or something qualitatively different was happening in Vancouver. Both conclusions were uncomfortable. The first suggested German industry might be falling behind in productivity. The second suggested Allied industrial methods might be superior to German approaches. The interyard rivalry created a continuous improvement cycle that benefited both yards and the entire Allied war effort. Every efficiency one yard discovered was quickly matched or exceeded by the other. Foremen shared ideas over lunch at local diners frequented by workers from both yards. Workers who moved between yards for various reasons carried techniques with them, formal knowledge transfer without formal meetings. The competition raised all standards simultaneously rather than creating winners and losers. By late 1943, both yards were operating at levels that would have seemed impossible just 18 months earlier. And they were still accelerating. Learning curves hadn't flattened. New efficiencies continued emerging from operational experience. The system was still improving. Observers from other Allied shipyards visited Vancouver to study the methods. United States Maritime Commission engineers spent weeks documenting processes. British Admiralty technical teams inspected facilities and interviewed management. Canadian military officials ensured the lessons learned at Vancouver were transferred to other Canadian yards under construction or expansion. The 4-week fleet had become more than ships. It had become a methodology, a proof that industrial-scale production methods could penetrate traditional crafts, a demonstration that systematic process control could achieve results faster than traditional skill-based approaches. And most importantly for the war effort, it had become a production system that was delivering hundreds of thousands of tons of shipping capacity to Allied convoy services faster than U-boats could sink existing ships. Railway dispatchers at classification yards across Canada chalked Canadian National Railway with increasing frequency. Each consists of a carefully assembled train carrying specific materials for specific purposes. Flat cars carried steel plates from Algoma Steel's Ontario mills. Gondolas moved structural shapes, I-beams, channels, angles cut to standardized lengths. Specialized cars handled boilers fabricated in Montreal and turbines manufactured at Sorel Foundry in Quebec. Hamilton foundries shipped deck fittings, winches, and windlasses in boxcars protected from weather. Every component was tagged with destination codes. Every item was scheduled to arrive within specific windows. The logistics coordination required to keep Vancouver's yards supplied approached military supply chain complexity. The statistics were extraordinary even by wartime standards. Approximately 1,100 railcars per month moved westbound carrying ship materials through established channels and priority routing. This translated to roughly 80,000 tons of steel and equipment per quarter arriving at Vancouver's rail sidings. The tonnage exceeded the total freight tonnage moving west in pre-war years for all purposes combined. The logistics web stretched across the entire country, touching dozens of suppliers, hundreds of component manufacturers, and thousands of workers who never saw a ship but contributed directly to ship construction. The coordination required systematic information systems tracking each item from manufacture through transportation to installation. Algoma Steel in Sault Ste. Marie ramped up production specifically for ship plates. The rolling mills operated continuously. Steel arrived from blast furnaces and went directly to rolling mills without intermediate storage. Plates emerged at precise thickness specifications required for different hull sections, thicker plate for bottom structure, thinner for superstructure and deckhouses. Each plate was stamped with heat number and composition for quality tracking. Montreal and Sorel specialized in propulsion equipment. Boilers were manufactured to standard designs with interchangeable parts. A boiler section manufactured in September could serve any ship under construction in October. Turbines followed similar standardization, not identical units, but families of compatible designs that simplified installation and future maintenance. Hamilton became the center for deck equipment production. Winches, windlasses, capstans, bollards, cleats. The thousands of fittings required for deck operations came from Hamilton foundries working 3 shifts. The foundries used standard patterns allowing rapid duplication. One pattern could produce dozens of identical winches. Quality control focused on critical dimensions that affected mounting and operation. Dominion Oxygen Limited recognized both opportunity and necessity in Vancouver's oxygen consumption. Industrial welding at Vancouver scale required oxygen supplies that exceeded British Columbia's entire industrial capacity in 1941. The existing oxygen plants that served hospitals, metal fabricators, and chemical processors couldn't meet even a fraction of shipyard demand. In 1943, Dominion Oxygen broke ground for a new dedicated plant at New Westminster, approximately 20 miles from Vancouver's shipyards. The facility was designed specifically to produce welding-grade oxygen and acetylene at industrial scale. The plant would be among the largest oxygen production facilities in North America when completed. The kit-of-parts approach extended beyond major structures to every aspect of ship equipment. Doors came in standardized sizes. 8 types covered 95% of requirements. Winches came in 4 standard capacities. Windlasses came in 3 sizes. Galley units were modular assemblies that arrived nearly complete. Berths were fabricated to standard dimensions. Ventilation fans came from approved manufacturers in limited models. Lifeboats followed naval standards with approved suppliers. This standardization dramatically simplified procurement, installation, and future maintenance. Vancouver's purchasing office could order by part number without detailed specification every time. Suppliers could manufacture inventory rather than waiting for specific orders. Installation crews knew exactly what to expect and how to install it. Future maintenance and repair would be simplified because replacement parts were standardized across dozens of ships. Block assembly supervisors could predict with precision when each item would be needed. A scheduler reviewing construction progress could determine that Block 27 would be ready for door installation on Thursday. The purchasing office had already ordered the doors weeks earlier. The railway had delivered them the previous week. They sat in the appropriate staging area awaiting Thursday installation. No one searched for materials. No one waited for deliveries. The flow was continuous. Railway sidings were organized to deliver components just in time to the appropriate shed or slipway. Siding 1 served hull plate fabrication. Siding 2 supplied deck structure sheds. Siding 3 delivered machinery and equipment. Each siding connected to specific work areas minimizing internal transport. Gantry cranes could unload directly from railcar to workstation without intermediate handling. This wasn't traditional shipbuilding procurement where each ship required custom ordering of thousands of unique components from dozens of suppliers with unpredictable delivery schedules. It was manufacturing logistics applied to ship construction. The yards operated more like automobile assembly plants than traditional maritime facilities, receiving standardized components on reliable schedules and assembling them into finished products using systematic processes. The Dominion Bureau of Statistics tracked the flow in monthly tables published as part of wartime industrial monitoring. The data was public, available to anyone including German intelligence. The statistics revealed a startling fact that couldn't be concealed even if secrecy had been desired. By year-end 1943, Canadian ship steel throughput exceeded the combined merchant shipbuilding output of Italy, Japan, and Germany. Three Axis powers with long maritime traditions, established industrial bases, and decades of shipbuilding expertise were being outproduced in aggregate by a single Canadian province that had possessed almost no shipbuilding capacity 3 years earlier. The comparison wasn't propaganda. It came from neutral Swedish shipping industry publications that tracked global maritime construction regardless of which side was building. The explanation wasn't mysterious to anyone studying the situation objectively. Centralized planning eliminated redundant procurement efforts that consumed time and resources in market economies. Rail priority codes prevented shipments from sitting in classification yards waiting for commercial traffic to clear. National production capacity was coordinated rather than competing. Different suppliers specialized in specific components rather than each attempting full product lines. The result was continuous flow throughout the supply chain. Cranes never waited for steel. Welders never waited for components. Assembly never stalled for lack of materials. The system approached theoretical efficiency limits, the maximum possible throughput given available resources. The supply chain itself had become a strategic weapon as potent as any gun or bomb. Germany couldn't sink ships in Canadian fabrication sheds. U-boats couldn't intercept trains crossing the prairies. The tonnage war was being won thousands of miles from the Atlantic, in steel mills and foundries and on railways connecting them to Pacific Coast shipyards. In the Kriegsmarine's Naval War Staff building on Torpedo, Signals branch officers compiled the latest B-Dienst intercepts. B-Dienst, Beobachtungsdienst or Observation Service, was Germany's naval intelligence unit responsible for intercepting and decrypting enemy communications. British naval codes had been partially compromised through cryptanalytic success and occasional captured code materials. German cryptanalysts could read enough traffic to track convoy compositions, routing, and losses with reasonable accuracy. A staff officer underlined a replacement ratio on the summary sheet before passing it up the chain of command. The numbers would reach Grand Admiral Donit's desk by afternoon, and the numbers were catastrophic for German strategy. Throughout the calendar year 1943 to date, U-boats had sunk approximately 5.3 million gross tons of Allied shipping. This represented enormous effort spread across hundreds of patrols. Thousands of torpedoes were expended. Hundreds of depth charge attacks survived. Dozens of U-boats were lost to escorts, aircraft, and mechanical failures. Each sinking represented tactical victory. German submariners demonstrated courage and skill consistently. Individual commanders achieved remarkable kill ratios. Tactics continued evolving: wolf pack coordination, night surface attacks, evasive routing to avoid patrols. The U-boat force remained dangerous and capable. But the strategic-level replacement figure told a different story entirely. The Allies had launched approximately 11.8 million gross tons of new merchant shipping in the same 1943 period. Replacement exceeded destruction by a factor of more than 2 to 1. For every 3 ships sunk, the Allies launched 7 new ones. The arithmetic was simple but devastating. Net Allied merchant capacity was growing, not shrinking. Every month the gap widened. Every quarter the surplus tonnage increased. The convoy system had more ships available than it needed for immediate requirements. Reserve capacity was accumulating. Grand Admiral Karl Donitz reviewed the figures personally during an afternoon briefing. His entire strategic concept rested on the tonnage war theory. The concept was sound in principle. If U-boats sank merchant ships faster than the Allies could replace them, eventually Britain would exhaust stockpiles and face starvation or industrial collapse. Unable to supply armies or sustain the civilian population, Britain would be forced to negotiate. The calculation depended on exceeding replacement rates. And that's what made the November statistics so devastating. The mathematics had inverted. Allies were replacing faster than U-boats could sink. A private note attributed to Donitz from this period states, "If these figures hold, we cannot win the tonnage war." This was the moment German naval strategy collapsed at a fundamental level. Not through defeat in any single battle. Not through loss of submarines beyond replacement capacity. Through arithmetic. Industrial arithmetic that showed the Anglo-American production base could replace losses faster than U-boats could inflict them regardless of tactical success. Vancouver represented a measurable share of Allied production. Not the largest share, that honor belonged to the United States East Coast and Gulf yards building Liberty ships and T2 tankers by the hundreds. But Vancouver's contribution was measurable, significant, and growing rapidly as the yards continued optimizing processes and expanding capacity. The Germans knew about Vancouver from multiple sources. Trade publications reported new construction. Intelligence intercepts mentioned Vancouver-built ships. Neutral observers in Canada reported shipbuilding activities. Swedish shipping journals tracked global maritime construction. The information wasn't secret. Canada publicized the achievement for morale purposes and to demonstrate Allied industrial capability. What German analysts struggled to believe was the speed. Their calculations said the reported construction times were impossible given known shipbuilding parameters. Either the reports were propaganda exaggeration or something fundamentally different was occurring that violated established industrial norms. Both possibilities were uncomfortable. Propaganda suggested Allied success was illusory, but then the ships appeared in convoy manifests with proper registrations and cargo manifests. Something different suggested German industrial assumptions might be obsolete, which implied broader competitive disadvantages across the industrial economy. From this point forward in the war, every U-boat patrol operated with negative strategic value in aggregate. Individual sinkings still mattered tactically. Ships sunk meant cargo lost, crews dead, immediate losses to Allied supply. But strategically, sinking individual ships no longer mattered if the Allies built replacements faster than sinkings occurred. Escorts and air cover now operated with reserve tonnage available. Convoy routing could prioritize safety over speed because additional ships provided redundancy. Critical cargo could be dispersed across multiple ships rather than concentrated in single vessels. The tonnage surplus provided operational flexibility that had been impossible in earlier war years when every ship loss hurt Allied logistics. The U-boat command tried to adapt tactically. Acoustic torpedoes targeted escorts rather than merchants, attempting to sink the protectors and create opportunities for merchant ship attacks. Schnorkel equipment allowed submarines to run diesel engines while submerged, avoiding radar detection while charging batteries. New submarine designs promised higher underwater speeds and longer submerged endurance. But tactics couldn't overcome mathematics. Even if every tactical innovation succeeded perfectly, the production gap ensured Allied tonnage continued growing. Germany would need to sink more than double current tonnage just to stabilize Allied capacity, and then still more to reduce it. The U-boat force lacked capacity for that level of destruction sustainably. The Battle of the Atlantic had quietly transformed from a desperate struggle with uncertain outcome into a statistical impossibility for Germany. The transformation wasn't sudden. No single event marked the turning point clearly. But by late 1943, anyone with access to production statistics and loss figures could calculate the inevitable result. Dönitz and his staff knew this by November. They couldn't acknowledge it publicly without undermining national morale and potentially facing consequences for defeatism. So officially the tonnage war continued. U-boats sailed on patrols. Tactics were adjusted. Hope was maintained publicly. But privately, German naval leadership understood the fundamental equation had shifted irreversibly against them. The Allies had won the tonnage war through industrial production faster than tactical excellence could counter. National Film Board cameras tracked SS Fort St. Pierre sliding into Burrard Inlet. The footage would appear in newsreels across Canada and the United States within days. Steam curled off welds that had cooled only hours earlier, still warm enough to vaporize moisture from the humid autumn air. The bow plating still radiated heat from final finishing work. Grinding smooth, inspection, and touch-up painting completed mere hours before launch. This ship had gone from first keel laying to launch in 17 days. 17 days from bare steel components delivered by rail to a floating hull ready for outfit and trials. Not 17 weeks, 17 days. Not 17 months, 17 days. The achievement seemed impossible by conventional shipbuilding standards. British yards averaged 6 to 8 months from keel to launch for equivalent tonnage. German yards required similar or longer time frames. Japanese yards were faster but still measured construction in months, not weeks. 17 days violated every established norm. Naval observers with stopwatches and clipboards had timed the entire process from beginning to end. They were present not to verify honesty. The yard's record was established, but to document methods for potential replication elsewhere. Their logs recorded an average rate of 1 hour per 50 tons of steel processed through the complete cycle. This included cutting plates to size, forming to hull curvature, welding into frames and shell plating, inspecting every joint, assembling blocks into larger sections, and finally joining sections into complete hulls. Mathematics seemed impossible until you understood the parallelization. Multiple blocks fabricated simultaneously. Multiple shifts working continuously. Multiple stations performing different operations on different sections. The critical path was much shorter than total labor because work overlapped extensively. Traditional calculation of man-hours per ton assumed sequential operations. Vancouver's simultaneous operations shattered that assumption. The outfit dock adjacent to the launchways had been pre-staged with every component needed for final completion days before launch. Winches sat on pallets with mounting bolts beside them. Anchors and chains were ready. Lifeboats hung from davits ready for installation. Galley equipment was created and staged. Navigation instruments were checked and calibrated.
Radio-gear awaitait d'installation.
Even paint for hull markings sat ready in proper colors and quantities. Nothing waited for procurement or delivery. Everything was ready when the hull arrived. The ship could proceed directly from launch to outfit without pause. Traditional yards had ships sitting at dock for weeks waiting for components to arrive. Vancouver eliminated that waste through aggressive pre-staging. Ottawa received a telegram that same day composed in bureaucratic language but conveying pride. Fastest ocean-going launch in Empire history achieved today. Fort St. Pierre launched a 17-day keel to water. Vessel proceeding to outfit. Estimated 3 weeks to trials. The message was accurate without exaggeration. No Commonwealth yard, not Britain with its centuries of maritime tradition, not Australia with its emerging shipbuilding industry, not South Africa with its strategic location, not India with its large workforce, had ever launched an ocean-going cargo ship in less time from keel laying to launch. The previous Commonwealth record had been 28 days achieved by North Vancouver ship repairs the previous month. Burrard had beaten its cross-harbor rival by 11 days. The rivalry was friendly but intense. Both yards pushed each other to greater achievements. German naval analysts reviewing the film footage through neutral intermediaries conceded in internal documents that this industrial tempo is unattainable under current blockade conditions. This assessment was accurate and important. Germany couldn't replicate Vancouver's achievement not primarily due to skill or knowledge limitations, but due to resource constraints. The British naval blockade prevented Germany from accessing many raw materials and components. Strategic bombing disrupted production. Allied submarines in Baltic and Norwegian waters threatened coastal shipping. The entire German industrial system operated under increasing stress that prevented the systematic organization Vancouver's success required. Enclosed prefabrication eliminated weather delays that plagued open-air yards. Rain, snow, wind, none affected work under the roof. Construction proceeded at identical pace in December as in July. This consistency was impossible in traditional yards where weather determined productivity significantly. Workforce scale substituted for individual skill through systematic process control. The workers were skilled by November 1943, no question. But the system didn't depend on a few master craftsmen. Dozens of competent workers following standard procedures produced results matching or exceeding traditional craftsmanship. The systematization was the revolution. Component staging eliminated idle time waiting for materials. Every block assembly station had the exact components needed for current work plus materials staged for next operations. Workers never stopped to find materials or waited for deliveries. The flow was continuous. Every innovation compounded. Weather elimination saved perhaps 10% of calendar time. Systematic training and tooling saved another 20%. Component staging saved 15%. parallel fabrication collapsed the critical path by 40%. The effects multiplied rather than added. A 35-day task became 17 days through multiple overlapping efficiencies. This wasn't incremental improvement within traditional methods. This was a fundamental transformation of the entire construction approach. The 17-day record stood as proof that modular construction at massive scale could overcome any limitation of climate, traditional skill requirements, or maritime construction traditions. The record would stand throughout the war. Other yards approached it. A few matched it. None beat it consistently. 17 days remained the benchmark, showing what was possible when industrial methods fully penetrated traditional crafts. Pilot cutters wove between assembled merchantmen filling Bedford Basin. 167 ships, convoy HX-300, the largest convoy of the entire war, prepared for Atlantic crossing. The sight was extraordinary even for Halifax, which had seen hundreds of convoys depart since war began. 6 of the ships bore Vancouver builders' plates. Dozens more came from other Canadian yards at Montreal, Quebec City, and smaller facilities. The remainder represented United States East Coast yards, Gulf ports, and British construction. The combined tonnage exceeded 1 million gross registered tons in a single convoy. The statistics told a story of complete industrial dominance. By mid-1944, Canadian yards overall had delivered 354 vessels totaling approximately 4.8 million gross registered tons. Vancouver represented roughly 1/5 of this total, substantial if not dominant. The Park ship program had delivered consistently month after month. Victory ship modifications were entering production with improved speed and cargo capacity. Specialized tankers and military auxiliaries supplemented standard cargo hulls. Royal Navy Trade Division officers, whose responsibility was managing convoy systems, tracked loss rates with precision. Statistics mattered because they determined whether Britain could be supplied adequately. In 1940, convoys had suffered catastrophic losses. Some convoys lost 20% or more ships during crossing. The worst convoys essentially ceased to exist as organized formations after U-boat attacks. By mid-1944, aggregate loss rates had fallen below 1% per crossing. Individual convoys occasionally suffered worse losses from concentrated attacks, but average rates had collapsed. A 1% loss rate meant 99% of shipped cargo arrived successfully. The difference wasn't primarily better escorts, though escort quality had improved dramatically. Purpose-built escort destroyers, corvettes, and frigates replaced pressed civilian vessels. Training improved. Tactics evolved. Radar and sonar became standard equipment rather than rare installations. It wasn't a better aircraft alone, though air cover mattered enormously. Very long-range Liberator bombers could reach mid-Atlantic gaps that had been safe zones for U-boats earlier. Escort carriers provided close air support directly to convoys. Aircraft could spot submarines and force them underwater where they couldn't track convoys effectively. The fundamental difference was replacement rate exceeding losses. When convoys departed with spare capacity beyond immediate cargo requirements, when multiple convoys could sail simultaneously covering different routes, when lost ships were replaced before loss reports reached Admiralty headquarters, the strategic calculation transformed completely. A Royal Navy logistics note from June 1944 stated in characteristic bureaucratic understatement, "Replacement capacity now occurs before loss accounting is complete." This had profound strategic implications beyond simple arithmetic. U-boats still operated throughout the Atlantic. They still represented danger to individual ships. They still occasionally achieved tactical successes, sinking merchants or damaging escorts. But the strategic-level threat had evaporated. Every torpedo expended represented resources Germany couldn't easily replace. Every U-boat lost meant experienced crews gone permanently. Training replacement U-boat crews took time Germany didn't have. Building replacement submarines consumed steel and labor desperately needed elsewhere as Allied bombing intensified and Eastern Front demands grew. The exchange ratio had become catastrophically unsustainable for Germany. Even successful U-boat patrols that sank multiple ships operated at net strategic loss because the expended resources exceeded any damage inflicted when measured against replacement rates. Escort groups equipped with high-frequency direction-finding gear and improved Type 271 radar now exploited the tonnage cushion aggressively. Rather than simply defending convoys passively and avoiding combat, escorts could pursue U-boat contacts aggressively. If a U-boat was detected, escorts could leave the convoy temporarily to hunt it while remaining escorts provided adequate coverage. The redundancy permitted aggressive tactics impossible when every escort was essential and none could be spared. Air cover from escort carriers provided continuous protection through the entire Atlantic crossing. Aircraft maintained patrols ahead and around convoys constantly. U-boats attempting periscope observations risked air attack. Surface transit became suicide in daylight. Even schnorkel operations left detectable wakes and radar signatures. Convoy routing prioritized safety over speed because schedule pressure had eased with surplus capacity available. Fast convoys still ran rapid schedules for urgent cargo. But regular convoys could take longer southern routes, avoiding known U-boat concentration areas. The flexibility came from having excess shipping capacity relative to critical needs. From summer 1944 onward, the U-boat fleet never regained any form of strategic initiative. Donitz tried new tactics desperately. Wolf packs shifted operating areas. New technologies entered service. Acoustic torpedoes that homed on propeller noise, improved schnorkels, eventually even crude radar detectors. Nothing worked at a strategic level. Individual tactical successes occurred. Specific ships sank. Specific convoys suffered losses. But the overall trend was irreversible. Monthly tonnage sunk declined. Monthly replacement tonnage increased. The gap widened inexorably. The Atlantic had been flooded with Allied shipping. The metaphor was apt. Like a flood overwhelming barriers, Allied production had simply exceeded German ability to inflict meaningful damage. And Vancouver's modular yards had contributed decisively to that flood through sustained delivery of quality tonnage faster than traditional methods could match. United States Maritime Commission engineers reviewed briefing slides projected on a conference room screen. The images showed Vancouver's enclosed fabrication sheds photographed from multiple angles. Diagrams detailed jig libraries and dimensional control systems with measurements and specifications. Photographs captured traveling cranes in operation and blocked assembly sequences at various stages. The presentation was titled simply, Lessons Learned from Canadian Modular Shipbuilding for Post-War Application. The audience represented serious industrial power and planning authority. USMC production planners responsible for American shipyard efficiency. Naval constructors from the United States Navy, Royal Navy, and smaller allied navies. Civilian maritime engineers from major shipping companies. Representatives from steel producers and equipment manufacturers. This wasn't academic discussion. These people would shape post-war maritime construction globally. They were studying Vancouver's methods for potential adoption in peacetime construction and for ongoing military programs still requiring merchant tonnage production through the war's end and into the occupation phase. The enclosed shed method received particular attention. American yards had adopted prefabrication partially, but often stopped short of fully enclosed facilities. The presentation demonstrated measurably superior productivity in enclosed facilities regardless of climate. Weather-independent construction wasn't just convenience, it was quantifiable efficiency gain. Adaptation for T2 tanker production was already underway at several Gulf Coast yards. The T2 was larger and more complex than Liberty ships, but modular principles applied equally. Components fabricated under roof, assembled in ways, outfitted rapidly. The methodology was technology neutral, applicable to any ship type with proper engineering. The block outfit discipline, completing all internal work before sections joined final assembly, was being codified in new construction manuals that would become industry standard. The principle seemed obvious once demonstrated but represented a fundamental departure from tradition where most outfit work occurred after launch. The systematic use of jigs and fixtures to eliminate skilled labor bottlenecks received extensive documentation for future reference. Traditional shipbuilding treated each ship as custom construction requiring extensive skilled labor making decisions continuously. Vancouver's approach embedded those decisions into fixtures, reducing skilled labor requirements dramatically without quality loss. A Naval Engineers Journal article from 1946 would later state, Vancouver proved that prefabrication and systematic process control could replace scarce skilled manpower with method and organization, achieving superior results faster. This was the deeper revolution beyond wartime emergency response. The crisis had forced innovation that revealed principles applicable far beyond immediate circumstances. Modular construction wasn't just faster, it was more consistent, more predictable, more scalable. Quality control was actually easier when work happened in controlled environments rather than exposed slipways. The lighting was better. The weather didn't interfere. Inspection access was superior. Defects were caught earlier when correction was simpler and cheaper. Training was accelerated when jigs encoded expert knowledge. New workers could achieve competent results within weeks rather than the years required for traditional apprenticeship. The systematization democratized skill without lowering standards. Scheduling was simpler when multiple parallel paths eliminated sequential dependencies. Project management could focus on coordination rather than constantly adjusting for weather, material delays, or skill availability. Observers from international yards took detailed notes. The presentations were unclassified. The information was shared freely. Vancouver's achievement reflected positively on Allied industrial capability generally. Spreading the methods strengthened global maritime construction capacity that would be needed for post-war recovery and trade revival. In the 1950s, Japanese commercial yards at Kure and Nagasaki would adopt Vancouver's enclosed modular methods almost wholesale for merchant construction. Japan's post-war shipbuilding industry would become globally dominant using principles first proven at scale on Canada's Pacific coast during wartime emergency. European yards would resist longer. Tradition died slowly in maritime construction. But eventually economic pressure forced modernization. Yards that didn't adopt modular methods couldn't compete on cost or schedule with yards that did. By the 1960s, modular construction was a global standard. What began as a desperate response to U-boat warfare became the foundation of modern shipbuilding practice worldwide. The crisis technique became the peacetime baseline. Future generations of ships, container vessels, tankers, bulk carriers, passenger ships, would all be built using principles first proven at Vancouver. The war had forced innovation by creating urgency that overcame institutional resistance to change. Industrial necessity had eliminated traditional constraints that protected established methods. Resources flowed to solutions that worked rather than solutions that were familiar. The result was a permanent transformation of maritime construction. Vancouver's contribution wasn't just ships delivered during wartime, though those ships mattered enormously to victory. The deeper contribution was methodology that would shape the industry for decades and eventually dominate globally. Modern container ships built in Korea or China in the 21st century trace intellectual lineage to innovations proven in Vancouver in 1943. The enclosed modular assembly, the systematic quality control, the parallel fabrication paths, all remain standard practice 80 years later. Sirens wailed across Vancouver Harbor announcing VJ Day. Victory over Japan meant the war's complete end. Europe had surrendered in May. Now the Pacific War has concluded. Slipways stood quiet beneath flags at half-staff honoring the dead even while celebrating victory. The urgent drumbeat of wartime construction that had pounded day and night for 3 years had finally ceased. Employment logs showed peak wartime staffing near 35,000 workers earlier in 1945. That number had already begun declining as war's end approached and contracts were completed or canceled. The immediate post-war period would see further rapid reduction as men returned to peacetime occupations and women faced social pressure to yield positions to returning veterans. But the physical infrastructure remained intact. The slipways were still there. The fabrication sheds, the cranes, the rail sidings, the oxygen plants all remained. The skills existed in thousands of workers who had spent years building ships. The organizational knowledge resided in managers and foremen who understood modular construction intimately. Final production tallies documented an achievement that seemed impossible judging by 1941 capabilities. Burrard Dry Dock alone had delivered 109 park ships plus numerous smaller vessels. Approximately 40 Royal Navy auxiliaries had been serviced, repaired, or constructed at Vancouver facilities. Total wartime cargo moved in Vancouver-built hulls was measured in millions of tons. Exact figures depended on how you counted partial loads and return voyages, but the scale was indisputable. Every weld had contributed to Allied victory. Every prefabricated block that slid down the ways had carried the war effort forward. The contribution wasn't abstract or theoretical. Those ships had carried the tanks that liberated Europe, the aircraft that bombed Germany and Japan, the ammunition that equipped armies, the food that prevented starvation. The yards faced an important choice that would determine whether the wartime achievement left lasting legacy or simply dissolved with victory. Demobilize completely and return to pre-war status as lumber ports? Or convert to peacetime merchant construction and repair work maintaining industrial capability? Ottawa's Reconstruction Committee received yard conversion plans within weeks of war's end. The proposals arrived quickly because management had been planning for peace since at least D-Day made Allied victory probable. Burrard management proposed transitioning to commercial merchant repair and selective new construction. North Vancouver Ship Repairs made similar proposals emphasizing repair and refit work for the expanding merchant fleet. The government faced pressure to reduce spending dramatically after 6 years of wartime expenditure. But decision-makers recognized the strategic value of maintaining maritime industrial capacity on the Pacific coast. Approval came for modernization funding to convert military shipbuilding facilities for commercial use. Not unlimited funding, peacetime budgets were tight, but enough to maintain capability. The facilities that had been designated temporary war plants in 1941 became permanent features of Canada's industrial landscape. Bureaucratic designation changed from temporary to permanent in procurement documents and planning files. The Pacific Coast gained a capability it had fundamentally lacked before the war: indigenous capacity to build, repair, and maintain ships without relying entirely on Atlantic yards or foreign facilities. The workforce gradually transitioned over months. Some workers left for other industries, logging, mining, construction, returning to farms. Many remained, applying wartime-learned skills to peacetime projects. The transition wasn't always easy. Peacetime pay rates were lower. Job security was reduced. Work pace was slower. Women who had proven themselves as welders, fitters, crane operators, and inspectors found some opportunities remained open, though many faced social pressure to yield jobs to returning men. The wartime opening of traditionally male occupations didn't fully survive into peacetime, but the door didn't close completely either. Some women remained in shipyard work, establishing precedent for future generations. The slipways that had launched emergency cargo ships at record pace now serviced commercial vessels moving lumber, grain, and passengers. Freighters, passenger ships, fishing vessels. The peacetime merchant marine required maintenance, repair, and occasional new construction. Vancouver's yards could provide all of those services. The infrastructure built for the wartime crisis found peacetime purpose. What had seemed temporary became permanent. Vancouver had transformed from a lumber port with minimal shipbuilding into a genuine shipbuilding city with infrastructure and expertise comparable to established maritime centers. Naval Service Headquarters compiled the final wartime shipbuilding summary in a brick building on Wellington Street. Statisticians from the Dominion Bureau of Statistics cross-checked figures against port records, Lloyd's Register entries, and individual ship files. Senior procurement officers reviewed final cost analyses comparing actual expenditures against original appropriations. The document that emerged told a remarkable story in dry bureaucratic language that couldn't completely conceal the achievement's magnitude. Average ship completion time is 1944, 38 days per vessel. This represented the mature state of the production system, not the early experimental phase with its learning curve, not the record-breaking individual ships that attracted press attention, but the sustained average production rate maintained month after month for an entire year. Total Canadian Pacific Coast tonnage delivered during the war: approximately 5 million gross registered tons. The figure excluded ships under construction when war ended and ships cancelled before completion. Cost efficiency averaged 30% below British comparators for equivalent vessels. Survival rate for Vancouver-built hulls reached 93% by the end of war, accounting for ships lost to U-boat attacks, mine strikes, storms, and all other causes. The summary concluded with an assessment that would be quoted in maritime engineering texts for decades. In Vancouver, the interval between blueprint and convoy readiness fell below that of any Allied yard outside Richmond, California. Richmond's yards built the famous Liberty ships using similar modular methods. Vancouver was in very elite company. This was the final judgment on competing industrial strategies between Axis and Allies. Germany had trusted U-boats and tactical military excellence. The Allies had trusted factories, logistics, and industrial arithmetic. Both strategies had been executed reasonably well by competent people. But only one approach could win the tonnage war that determined Atlantic control. The U-boat force had fought with extraordinary skill and courage throughout the war. German submarine crews faced terrible odds. Over 70% of U-boat crew members died during the war, among the highest casualty rates of any military service. Their commanders innovated continuously: wolf pack tactics, night surface attacks, acoustic torpedoes, schnorkel systems. The tactical excellence was undeniable. But courage and tactical innovation couldn't overcome fundamental industrial mathematics. When one side builds ships faster than the other can sink them, the strategic outcome becomes inevitable regardless of tactical proficiency. The arithmetic was simple. Replacement rate exceeded loss rate. Therefore, net Allied tonnage grew. Therefore, Allied logistics improved. Therefore, Allied military operations strengthened. Therefore, Axis defeat was certain.
Escorts mattered, destroyers, corvettes, frigates hunting U-boats protected convoys effectively.
Radar mattered, detecting submarines before they reached attack positions saved ships. Code-breaking mattered. Reading German naval communications allowed convoy routing to avoid concentrations. Aircraft mattered. Long-range bombers and carrier aircraft suppressed U-boats throughout the Atlantic. But industrial tempo made everything else decisive. Without adequate shipping, escorts had nothing to protect. Without replacement capacity, every loss hurt Allied logistics critically. Without industrial margin, tactical losses could become strategic defeats. Vancouver's contribution was measured in hundreds of ships, millions of tons, and thousands of successful convoy crossings. Each ship carried food that prevented starvation in Britain, ammunition that equipped armies liberating Europe, fuel that powered aircraft bombing Axis industry, vehicles that supported offensive operations from North Africa to Germany, medicine that saved lives in field hospitals. The cargo was life itself for Britain during the darkest years. The modular yards on Canada's Pacific coast had turned welding schedules and prefabrication efficiency into strategic weapons more powerful than battleships or bombers in some respects. They had proven conclusively that modern warfare was ultimately decided by industrial capacity at least as much as battlefield prowess. Tactical excellence without industrial support was insufficient. Strategic vision without production capacity was meaningless. Germany's military tradition, tactical skill, and strategic planning couldn't overcome Allied industrial dominance once that dominance reached full mobilization. Germany lost the Atlantic not primarily to admirals or submariners, though both contributed significantly. Germany lost to welders who could turn steel plates into seaworthy tonnage faster than U-boats could reload torpedoes. Lost to railway workers moving steel westward across Canada. Lost to steel workers at Algoma rolling plate. Lost to engineers designing jigs and fixtures. Lost to planners coordinating supply chains. Lost to a system that could mobilize industrial capacity at scale and sustain it for years. That was the statistic that ended the war. Not any single battle. Not any particular weapon. But the relentless arithmetic of industrial production exceeding destruction until victory became mathematical certainty rather than hopeful possibility. If you value fact-based history built from archival records and verified statistics, consider supporting the channel. Every story represents hours of research into original documents, wartime reports, and official records, ensuring that what you hear reflects what actually happened, not dramatic fiction. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive and honors those who served.